we're going to study some inference procedures for a new population parameter that's of interest. And that parameter is what we call the population proportion. And we give it the unhelpful symbol p, but we'll keep all the different p's straight. And so just to try to give you a bit of intuition, the population proportion essentially asks what portion of the whole population is successful. Now, success is dependent on what we define it as, but as a very simple example, we could say something like this. The proportion of Vancouverites who cheer for the Vancouver Canucks is 0.753. So in this example, success means cheering for the Vancouver Canucks. And we are going to take a look at a variety of different problems that involve quantities like this. Now, we could define the proportion as the number of successes in the entire population divided by the size of the population. And what that tells us is that we could get any value for p ranging from 0 all the way up to 1. So here x is going to be the total number of successes. And we'll note that the fewest number of successes we could have is 0, and the greatest number of successes we could have is everybody in the population, capital N. So that means this parameter is always contained between 0 and 1 inclusive. You could have a population parameter of a proportion of 0, and you could have a population proportion of 1. It can't get any smaller than 0, and it can't get any larger than 1. And now, in this case, we don't know what the parameter p is. All we know is that we've got a population that's filled with some random variables. They're all going to be IID. We have no idea what they are, but the only thing that we are of interest here is that these xi are what we call Bernoulli random variables. That means there are two outcomes. And the random variable here measures success or failure. So xi could be 0 is failure, and xi equals 1 is what we would call success. Now, we talked about such variables way back when we talked about the binomial distribution. Now, it's a simple matter to take these two outcomes and calculate the expected value here. The expected value is just going to end up being little p, the population proportion. How many people are in favor, or what are the chances of success? The variance is also straightforward to calculate. It would be p into 1 minus p. So if you forget how to do that, I urge you to stop the video, pause, and go remind yourself how that comes about. But essentially, each one of these dots in the population represents an individual, and we are treating them as a Bernoulli random variable. We are interested in the output 0 or 1. Do you have success or do you have failure? Now, our goal is to determine this value of p. Now, with all inference procedures, you can never truly determine the value. The best you can do is estimate it. And so the theme of statistical inference is that you take a sample. So we are going to estimate this p using a sample. And it's always going to be a random sample so that we can treat the variables independent of each other. And it will have a size little n here. And so our sample will contain these random variables from x1 up to little xn. And now the idea here is that we want to estimate using a new parameter. So this will be our estimator. We are going to say that this function, this new random variable, is called the sample proportion, and we'll denote it with a capital P hat. And this capital P hat will be the total number of successes in the sample divided by the sample size. So in terms of notation that we've used before, this is going to be capital X over N. And here, this capital X is the total number of successes. And from earlier in the course, we know that that has to follow a binomial distribution, where it's distributed n binomial NP. So this new estimator sample proportion is the tool that we are going to use to help us say something about the population parameter. Now we need information about this estimator p hat. What's its expectation? What's its variance? And what is its distribution? How is it distributed? In order to perform inference procedures, we need the answer to all of those questions. Now, fortunately, we have the tools to be able to answer all of these things. So note, first of all, if we define this sample estimator as the total number of successes divided by the sample size, that means we can apply our properties of expectation and very simply come up with the following. Now, since X follows a binomial distribution, N and P related to the sample size, we know from chapter 3.1 what this is. This is going to be NP divided by N, and so we will end up with a P. And that means this P hat is an unbiased estimator of the population proportion P. So that's good. This calculation that we are performing, quite rightly, is centered on the thing we are trying to estimate. So this is good. So we've figured out the expected value of this tool that we're about to use. Now, its variance. The variance of this P hat, we can once again apply properties that we've learned earlier in the course. Remember that if there's a scaling of a variable up front, you can take it and square it, and then it ends up simply being the variance of this random variable. Now, from chapter 3.1, for a binomial variable, we once again discussed how this works. So for a binomial variable, the variance was NP 1 minus P, and because of this scaling up front, we will end up with a P 1 minus P all over N. So this estimator, we can figure out its variance, P 1 minus P over N. That's important because in the third step here, we need to determine the sampling distribution for this P hat. So what is the sampling distribution for this estimator P hat? Now, this depends on essentially what we've got here. Now, note, the underlying distribution for our sample and for our population here is binomial. So we know that the total number of successes in the sample is given by this X, and we know that the X is binomially distributed, and it's related to the sample size N and this unknown population parameter P. Now, by definition, we know that this P hat, the sampling estimator that we are trying to use, is simply X over N, and that tells us that X is equal to N P hat, and that means that N P hat has to also be binomially distributed. Now, this might look a little strange to you. You might say, well, what's the distribution for P hat? It's not so straightforward to determine, but with a little bit of thought, you can understand why the result is going to be the way it is here. And so what I mean by that is, if X represents the total number of successes in our sample, it goes from 0 to N, and at the same time, P hat is just x divided by n. So we'll have 0 over n, 1 over n, 2 over n, and this will go all the way up to n over n. Now, since x is binomially distributed, that means if we wanted to take a look at a bar graph of its mass function, it would have some sort of value, right? We would have a 0 and a 1, and we'd end up with some sort of picture. Now, the specific picture that we get would depend very much on the values of n and p, but what this result is telling us here is that since np hat is equal to x, it's also binomially distributed. And that means if we wanted to underlay an axis down here with p hat values, we would get exactly the same bars and exactly the same locations and exactly the same heights for the values of p hat. So for all intents and purposes, we can say that np is binomially distributed, and that will give us a relationship for p hat as well. That means p hat will also be binomially distributed with this n and p, but we'll have this extra addition that we've determined its sampling parameter here. We've got this p, and we know that its variance is just p 1 minus p over n. So this will turn out to be the exact sampling distribution. So this is what we will call the exact p hat distribution. It's a discrete distribution. So when we use R, we can essentially use a binomial distribution with our number of successes and our n and our p. I'll come back to that a little bit later. If we ever need to perform calculations with the exact distribution, it's possible. But for chapter 10 here, for this section, we are not going to rely on the exact formula. So we don't use the exact distribution for p hat. So why not? And the main reason here is that it's really inconvenient to develop formulas for our inference. Now, take this with a little grain of salt. This was a lot more valid back when it was difficult to get access to computers, calculators, that sort of thing. And there are some theoretical ideas that were used to help stats people make progress. So instead, what we are going to do is, for the purposes of illustration and developing some theory, we are going to use an approximation for this p hat distribution. Now, you probably can guess where this is going to come from, and this is going to be related to the central limit theorem. So this is what we are going to call a large sample approximation. So the underlying message here is that the sample sizes we are dealing with are going to be large enough for these approximations to hold. So central limit theorem said that we probably need n greater than 30. Now, there were some other conditions in the textbook about when you can replace a binomial with what's coming up here, a normal. But either way, we are going to assume that these conditions hold. So we know that if we've got something in the binomial distribution, we said that it was approximately the same as representing it by a normal distribution with the same mean and this scaled variance. So if you need, you can go back to chapter 5.3 and review that. But essentially, that is how we can connect this discrete distribution into a continuous one. Now, the idea here is that p hat you could think of as np hat over n. And the reason that I'm doing that is that this is x over n. So it's essentially going to be a scaled normal distribution. So it's going to be a normal distribution, the one that you get from here. So the np 1 minus p. But because of this n in the denominator, you have to scale things appropriately there. So no surprise, the approximate distribution for p hat is going to be a normal distribution centered at p, and it has this standard error, p 1 minus p over n. And this is the one that is going to be used exclusively. So when you go ahead and you perform your homework and you do all the things in the test and the questions, it's going to be this approximate distribution for p hat. And this is the one that we are going to use to develop our inference formulas. So we are going to develop our inference using this approximation.